Hi, and welcome to the lecture on atomic structure and models. It's crucial that you get an understanding of the basic structure of an atom and the use of models to represent that structure if you're going to understand ionic and covalent bonding in later lectures. To begin with, we look at just the general structure of an atom. In general, the structure of an atom, you have a core nucleus made of protons and neutrons, and electrons orbiting around this core. You're looking at something kind of like planets orbiting around the sun via the planetary model. Now in the nucleus, the protons are positively charged, the neutrons are neutral, and around the nucleus the electrons are negatively charged. Now the protons, neutrons, and electrons have a mass. It's very minuscule, and we're going to measure that mass just by calling the weight of one proton 1 Dalton, or 1 AMU. The weight of one neutron is also 1 Dalton, and the mass of the electrons down at the bottom we are going to ignore because that is 1/2000th of 1 Dalton. So if you had an element, let's say hypothetically, that had 10 protons and 10 neutrons, then its mass would be 20 Daltons, 10 plus 10. Looking at a few models here, you've got the planetary model on the left of your screen and the orbital model over there. Your planetary model shows the nucleus with the protons in red and the neutrons in yellow and the electrons in gray orbiting around the nucleus, kind of like planets around the sun. The orbital model is much more realistic. The electrons can't be necessarily pinpointed or orbit, like planets do around the sun or anything like that. The periodic table is going to be your key. You have to understand the periodic table. We'll come back to it periodically. You have 18 groups running across. Each group has very similar properties. So if you look over here at, say, this group 1, lithium, sodium, potassium, these are all soft, white, shiny metals. Alright, with the exception of hydrogen here is one of our little kickouts for that group. So they have similar properties. This would be group 2 and group 3, and you run all the way across here to group 18, which we'll call our noble gases. If you pick one of these guys out and take a look at it, you'll notice there's some information found. You have the name of the element, you have its atomic weight. Now atomic weight is the number of protons plus the number of neutrons. So you're looking at the atomic weight for oxygen being 16. That means it has 8 protons and 8 neutrons. The way I figured that out is by looking at the atomic number. Your atomic number on your chart, the way they are numbered, hydrogen's number 1, helium's number 2, lithium 3, 4, 5, 6, 7, 8. Oxygen has 8 protons. That's its atomic number. This number does not change. Atomic weight changes depending on isotopes. So atomic number, number of protons, atomic weight, number of protons plus the number of neutrons. So if you subtract the atomic number from the atomic weight, you find out how many neutrons there are. So if I were to say how many neutrons are there in carbon, for instance, you go look over here at carbon, you see its atomic weight's 12, round down. 6 minus 12 is 6. So carbon would have 6 protons, atomic number, and 6 neutrons for a mass of 12. Your atomic weight is your Dalton number. So carbon would weigh 12 Daltons, oxygen would weigh 16 Daltons. That's why when we do molecules, you can look at them and say, well, if you combine carbon and oxygen together, you'd have 16 plus 12. You'd have a total weight there of 28 Daltons with just a C and O. That'd be carbon monoxide. Very dangerous. The BOHR model is a model we're going to use a lot in class. The BOHR model has some rules you have to follow. The first thing you want to notice is that proton number is equal to electron number, and we're pretending atoms are in a pure state. Then you have energy levels that represent where the electrons go. And your first energy level is just represented as a circle around the nucleus, which you can see here, and it can hold only 2 electrons max. Energy level 2 can hold up to 8. Now that's a max. It does not have to hold 8. It can hold up to 8. And then your next energy level 3, can also hold a max of 8, but you notice sodium only has 1 electron in it. So the maximum number is 8. Now if you keep in mind your rule, protons must equal electrons, Sodium has 11 protons and 12 neutrons in its nucleus, so this would be a mass of 23 Daltons. You've got 2 protons in your first energy level, 8 in your second, 8 plus 2 is 10, and you've got 1 in your third, so that'd be 11. 11 protons, 11 electrons. Check out chlorine. 17 protons, 18 neutrons in the nucleus. Remember, protons positive, neutrons neutral. You've got 2 electrons in the first energy level, 8 in the second energy level if you count them up, and 7 in the third energy level. Here's your little one here that doesn't have a buddy. So it's 17, right? 2 plus 8 is 10, plus 7 is 17. You follow these rules, you can now draw any of the elements on the chart just using these simple rules for the Bohr model. So if you were to pick out, a few in practice, just follow these rules. Practice makes perfect. The electron dot model is a little different and a little simpler than the Bohr model. You don't have to include the proton-neutron number. What you draw is the chemical symbol for the element and the number of valence electrons. Each dot represents one valence electron. Now, valence electrons are the electrons that are in the last energy level, your outermost electron shell. These are the electrons that control all of bonding, who sticks to who. Na will stick to Cl and form NaCl, which is salt, and one of the most common most common compounds on planet Earth. 2 H's and a O make water. So all of that is explained by the valence electrons. Real easy to find the valence number if you use the periodic table. If you look at elements that are in group 1, like lithium and sodium and all these guys, they all have 1. Elements in group 2 all have 2. Elements you find, boron, all these guys, group 13 has 3, group 14, 4, 15, 5, group 16 running down your periodic table, 6, group 17, 7, and group 18 will